Hey everybody, my name is Jennifer Douglas and I'm an AP Chemistry teacher from Georgia, and I'm here to walk you through the solutions to the AP Chemistry practice exam for 2020 that Marco has provided for you. And so we're just going to go ahead and get started right away. We are told for the first question that there's 3 possible structures for carbon dioxide, and we're given those 3 Lewis structures, and we are asked to evaluate. Actually, we're told that the one on the left is the most stable, and we're asked to explain why the structure on the left is the most favorable representation and to justify your answer using formal charges. And anytime that you see a question that starts off with telling you how to approach the question, you know exactly where to go. So we're told to start with formal charges. Don't come up with your own way of doing something like this. And we know that formal charge is a way for us to evaluate Lewis structures to see which one is the more favorable one. That's the purpose of formal charges. And it's a way of looking at electron distribution in molecules. It's different than oxidation numbers. So we use formal charge specifically for evaluating different Lewis structures and to find out which one is more likely to be the one that occurs. All right, so the way that you calculate formal charge is that you take the number of valence electrons that an atom has and you subtract from it its assigned electrons in a structure. So starting with the structure on the left, we see that the first oxygen right here is we know that it comes with 6 valence electrons. And we can count the number of electrons which we assign it by counting the number of lone pairs of electrons, because each one of those belongs to that oxygen. So we see that there's 1, 2, 3, 4 electrons that it has on its own. Those are lone electrons or lone pairs of electrons. So it's got 2 lone pairs, which give us 4 electrons. And then we also see that it's sharing a pair of electrons with carbon. And so when you're doing formal charge, whenever you have a bond, then one of those electrons goes to one atom and the other one goes to the other. So we have 1 electron going to oxygen for that bond and for this one. So we can see that there's 1, 2, 3, 4, 5, 6 electrons which are assigned it. So we have 6 valence electrons minus 6 that are assigned, which give us a 0 for the formal charge for this oxygen. And so we had 6 valence electrons minus 6 assigned, and that gives us a formal charge of 0 for the oxygen. And now we're just going to go through and do the same thing for the carbon. So we know that carbon has 4 valence electrons. We can see that carbon has 4 electrons assigned to it because it has 4 bonds. So we get 1 here, 2, 3, 4. 4 minus 4 is 0, so the formal charge on the carbon is 0. And then we have the next oxygen, which you can see looks just like the one that was on the left-hand side of the molecule. There are 6 valence electrons minus 6 assigned, which gives us a formal charge of 0. So this first structure is looking pretty good because in terms of formal charge, you want to be able to minimize the charge. The lower the charge, the better. And we know that we want the most electronegative atom, which in this case would be oxygen, to have the lowest formal charge on the molecule, which it does since they all are 0. So this structure is looking pretty good. And we're already told that that one's the one that's correct. But let's go ahead and check the formal charges on the next 2. So for the second molecule, we have the first oxygen has 6 valence electrons, and we have 5 electrons assigned to it. We can see that there's 1, 2, and then 3, 4, 5, which gives us a charge of 1. That's already not as good as the first molecule. Carbon has 4 minus 4, which gives us 0. And then the oxygen has 6 valence electrons minus 7 assigned, which gives us a formal charge of -1. Let's go ahead and finish the formal charges for the third molecule, and then we'll talk about why the one on the left is better. So for the one on the right-hand side, we have oxygen, which has 6 minus 6 is 0. We have oxygen in the middle this time, so we have 6 valence electrons minus 4 assigned electrons, which gives us a formal charge of 2. And then the carbon has 4 valence electrons minus 6 assigned, which gives us a charge of -2. So now we have to choose which one of these is the best. We go back to the question, justify your answer in using formal charges. We now know what the formal charges are. How do we choose which molecule is the best? Well, I mentioned the two qualifications. We want to minimize the formal charge. So looking at the structure on the left, we see that it does have, all of the atoms there do have a low formal charge because they are zero. And anytime you can get zero or less, that's good. The second molecule has a formal charge of 1 on the oxygen. So that's already not as good as a 0. And there's something else that's the matter with that. I'll tell you in one moment. And then over here, we see that there's an oxygen with a 2 here. So that's already a problem. But also the second thing is that we want the most electronegative atom, that's oxygen in this case, to have the lowest formal charge. We can see that it does not here. Carbon has a lower formal charge than the oxygen does, so that's out, absolutely. And the same thing over here, we can see that we have an oxygen with a 2, which is a much higher number than -2, so that throws that one out as well. So we have to have the most electronegative atom is going to be the one that's going to be attracting the most electrons. So it's going to arrange itself a way where it can get the most of these. Now, our final answer could be, after we've calculated the formal charges or determined those, we can say that the structure on the left provides for the two things that I mentioned. The formal charges are minimized on all the atoms, best in that structure that's on the left, and also the most electronegative atom. It allows it, that would be oxygen in this case, to have the lowest formal charge. Since they're all 0, that made that easier here. But it did not allow, these two structures here and here did not allow oxygen to get the lowest formal charge. So that's A. Okay, moving on. So we now have, let's see, letter B, where we're given some bond energies, and we're asked to figure out what the delta H, the enthalpy of the reaction is. For the reaction where we have 2 carbon dioxides yielding 2 carbon monoxides and an oxygen. So the idea behind bond energy is this. You have to put energy in to break the reactant bonds. So we know in a chemical reaction, bonds are breaking, new bonds are forming in the products, and it always takes energy to break the bonds of the reactant. So that's going to be the energy in part. And then on the product side, energy is released as we allow an attractive force to form. So again, it takes energy, it's energy in on the reactant side to overcome an attractive force, and then there's energy released on the product side. So we are given some bond energies here, and we have to figure out how much energy we're putting in to break the reactant bonds and how much energy is being released when the product bonds are formed. So we need to start by figuring out how many bonds there actually are, and that's where we have to pay attention to the stoichiometry. Notice that there's 2 carbon dioxide, so I'm writing 2 carbon dioxide Lewis structures down here, and I know that I'm going to put energy in to break those bonds down here. Let me pick up my pen. So I'm putting energy in to overcome the bonds of the reactants. And then on the product side, I'm going to have energy released. And I'm just going to use my bond energy table to figure out how much energy is actually involved. So if I look at my first question, I'm given a bond energy of 741 for a carbon-oxygen double bond. In my mind, I was thinking it was closer to 800, but that's okay. You just go ahead and go with the data that's given to you. So we have 741 kilojoules being put in to break one of those bonds right here. But we can see that there's also a carbon-oxygen bond here, and there's one here, and there's one here. So we have 741 being put in to overcome that attractive force and break those bonds. On the product side, we have energy being released. So carbon monoxide, we have 1080 kilojoules, and the oxygen double bond is 798. So now it just becomes a matter of us summing up what's there. So on the reactant side, we have 4 carbon-oxygen double bonds. So it's 4 times that 741 number that we were given. And that gives us 2,964 kilojoules per mole. That is being, that we are putting in, energy that's being put in. On the product side, we have 2 of the carbon-oxygen triple bonds. So that's 2 of the 1080 kilojoules per mole. And then we have 1 oxygen-oxygen double bond, that's 498. And when we sum that up, we get 2,658. So now what we have to do is say that we put in this much energy was released. So whenever you're given bond energy, the equation that you're using is that delta H of the reaction is bonds broken, the amount of energy you put in, minus bonds formed. So we can see that it is going to be bonds broken. There's 4 times the 741 that we had. That was the 2964, minus the energy that's released, or when the bonds are formed. And so that's 2 times 1080 plus 498, which gives us 2658. And altogether, that gives us 306 kilojoules per mole of reaction. So we can see that we had to put in more energy was put in to break the bonds of the reactants than was released when the bonds of the product formed. And so this would end up being an endothermic reaction because we had to put more energy in than we got out. Okay, letter C now. We're asked to, it's another thermochemistry question. We have 2 aluminums and some iron oxide making iron and aluminum oxide. And we are given heats of formation value this time instead. And we are asked to calculate the heat of formation. We actually told a student to calculate the heat of formation to be 820. And we are supposed to find out if the student was right or wrong. So that means we're going to have to go ahead and figure that out ourselves. So notice that this time we're given delta H for the reaction. And we're asked to find the heat of formation. Now heat of formation, that is the amount of energy that's associated with forming 1 mole of a compound from its constituent elements in their standard state. And so notice that the aluminum and the iron have heats of formation of 0. That's because they already are elements in their standard state. And then notice the question mark there. So we are going to be looking for the heat of formation of iron oxide. That's iron 3 oxide. So here we go. The heat of delta H for the reaction is going to be the heats of the formation of the products minus heats of formation of the reactants. And so we need to look at the reaction itself. And I would recommend doing this. Take your reaction and go ahead and write in the heats of formation that you are given in that table above it, because you're using so many numbers, you don't want to copy down something incorrectly. So I'm putting a 0 above the aluminum and the iron. I'm looking for the heat of formation for iron 3 oxide, and I'm given negative 1680 as my heat of formation for aluminum oxide. So there we go. Those are the assigned values. And now I'm going to take the products. Now this is where you have to be careful. You want to take the heat of formation of the products over here, products minus the reactants, and just plug those into that formula. So we can see that we were given delta H for the reaction being negative 860. We got that because we were given that value right up here. And when we do the products, that's 2 irons, so it's 2 times 0, plus the aluminum oxide number. There's our 1680, negative 1680. So there's our products, minus the heats of formation of the reactants. It's 2 times 0 for the aluminum, plus the number that we're looking for, the one for iron 3 oxide, which is right here, the X. So now we're just going to go ahead, rearrange, and solve for X. So we get that negative 680 is negative 1680 minus X, and we end up with a value of X for negative 820 kilojoules per mole. Now, let's go back and look at what we were actually asked. You always want to make sure that you go back and finish answering the question and don't just move on, because you're not going to get your final point that way. We are told that the student came up with a number of positive 820. Was the student correct? No, the student is not correct. The student should have gotten negative 820. So probably what the student did was did reactants minus products, which is not what you're supposed to do, instead of doing products minus reactants. Okay, so that is letter B. No, that is letter C. Let's go on to D. Now we're told at high temperature, nitrogen gas and oxygen gas will react to produce nitrogen monoxide, as represented below. Okay, now we are asked to write the Kp expression for the reverse reaction. Okay, the reverse reaction. I wouldn't try and do this in my head. I would go ahead and write the reverse reaction. Too easy to make a mistake if you don't do that. So there's the reverse reaction. And now we're going to go ahead and write the Kp expression. So we know that that's going to be the products over the reactants raised to their coefficient powers, and there's your Kp expression. Okay. And notice that just as a comment, if you were asked for Kc, make sure that you use square brackets, because we know in chemistry that the square brackets represent concentration. Here we're told pressure, so we don't use square brackets there. At the high temperatures, well, we just said that. We've got this reaction below, and now we're moving on to II. A student is provided a rigid evacuated vessel and injects samples of N2 and O2, if I can talk. All right, then the student raises the temperature to 1,000 degrees, where the initial partial pressure of N2 is 3 atmospheres, and the partial pressure of O2 is 0.81 atmospheres. And once the system reaches equilibrium, the partial pressure of NO is 0.061 atmospheres. Calculate the value of Kp of the reverse reaction. Okay, we know we're dealing with equilibrium here because we're calculating a K. So we want to go ahead and set up a rice table or an ice table, depending on how your teacher taught you that. So we have our reaction right here, and I'm going to go ahead and write it in the forward direction for right now. I'm told that initially I have 3 atmospheres of N2 and 0.81 for O2, and notice that NO is not mentioned. If it's not mentioned, it means it's not there, so go ahead and assign it a value of C. So there we go. I've got my initial states, my initial pressures there. And now to figure out the change, notice the stoichiometry. There's 1 N, 1 O, and 2 NOs. So my change is going to be X, X, and 2X. There's my mole ratios. And now I have to figure out which is going to be my minus X side, which is going to be the plus X side. And notice that I'm starting with 3 atmospheres and 0.81. Since I'm starting with moles on that side, that has to be the minus side. I can't start with 0 and use some of the 0 up. So that gives me minus X on my reactant side, plus 2X on my product side. And that will give me 3 minus X, 0.81 minus X, and 2X. Now, I have to be given one more piece of information to move any further with this question, and it's right here with the 0.61 atmospheres. That's the partial pressure of NO at equilibrium. So I know that 2X is the same thing as a value of 0.061. So if 2X is 0.061, then I know that my X is going to be 0.0305, and now I can substitute in the X's and solve. So these are the values that I get for equilibrium for my N2, my O2, and my NO. Now let's see, I'm not done. It's asking me to calculate the value of Kp for the reverse reaction. So my reverse reaction, remember we were asked earlier to provide the Kp expression for the reverse reaction. So now I'm just going to plug in the values that I just found, and I will end up with a Kp value of 620. The reason I went to 2 significant figures is I'm going to say that temperature, I'm going to pretend that had a point there because I'm assuming that we didn't want to do 1 significant figure. I see there's 3 significant figures for my N2. My O2 is 0.81, and those are the only numbers really that I'm doing calculations with. So there's my 2 significant figures. That's going to limit my question. There's also 2 significant figures here. So I left my answer with 2 significant figures as well. All right, that brings us to question number 2 now. So we are told that the elements in group 17 exhibit different states of matter when observed at room temperature. Chlorine is a pale green gas and iodine is a gray solid. Okay, so already in my mind I'm talking about states of matter, I'm thinking intermolecular forces. And let's see, letter A says, letter A, explain this observation in terms of the type and relative strength of the intermolecular forces, there it is, in each substance at room temperature. Okay, so notice again that they're telling us exactly how this question is to be answered. We are told, let me pick up my pen here. We are told to identify the type of intermolecular force, and then we are told to compare the relative strength. So when you're given this much information in the prompt, go ahead and use it. It's guiding you on exactly how you're supposed to answer this question. All right, so let's think. We've got chlorine and we've got iodine, Cl2 and I2. And when you think about the Lewis structures of those, there's a single bond between them. They each have, on each end of the molecule. There's 6 lone pairs of electrons around each one. So we know that they're both nonpolar molecules. So if they're both nonpolar, then the only intermolecular force that's present is London dispersion forces. Okay, so there we go. I've said that I2 and Cl2 are both nonpolar. Therefore, both substances have London dispersion forces as their intermolecular force. And now I have just identified the type. I've answered that part of the question of intermolecular force that's present. So now let's go ahead and think which one's going to have the stronger intermolecular force. So I see that I2 is a solid, whereas at the same temperature, chlorine is still a gas. So I know that that means, use the data that's given to you. I2 is a solid. It has the stronger intermolecular force. So you already know that that means that the London dispersion forces in I2 have to be stronger than the ones in chlorine, and then you just have to figure out why. So we can state the LDFs between molecules of I2 are stronger than the LDFs between molecules of Cl2. Notice that I've made a comparison there. And also, I've also used the term between because your grader is always going to be looking to make sure that you understand that intermolecular force exists between two molecules. It's not the intramolecular force that's between two atoms within something. It's not a bond, it's a force of attraction between two different molecules. So anytime you can use the word between when you're talking about intermolecular forces, that's a good thing because it shows that you know what you're talking about. So I know that LDFs in I2 have to be stronger because I2 is still a solid. That means it's going to take more energy to overcome that intermolecular force and allow it to become a liquid or a gas. So why would that be? Well, I2 has a larger electron cloud, and because it has a larger electron cloud, I2 has more electrons, the electron cloud is larger. Therefore, that makes that electron cloud more polarizable than Cl2's. And because it's more polarizable, there's going to be more of a chance that there's going to be a temporary shift where the electrons are more on one side of the molecule than the other side. And that gives us that temporary polarized cloud. And so that probably answered the question right there. But you could go ahead and wrap it back into the fact that the stronger LDF is sufficient to allow I2 to exist as a solid at room temperature, and the weaker one of Cl2 results in chlorine being a gas, because not as much energy was required for chlorine to overcome the intermolecular force. But I really think you had that question answered right where I have the blue line. Okay, that's letter A. Now we have letter B. We've got polymers are produced from alkenes in which one or more hydrogen atoms have been replaced by a fluorine atom. Okay, and we are given two important members, PTFE, and also known as Teflon, and PVF, which is the structure that's shown on your left. And there's each one drawn for you. And we have to predict which one would have the higher melting point and justify your answer. Okay, we're talking about melting points. That means we know that we've got to start thinking in terms of intermolecular forces. So we see that these are both repeated structures. And if we look at the PVF, I can see that that thing is going to have one fluorine that's replaced a hydrogen here, and the rest of the hydrogens have not been replaced. So I can see that that's a polar molecule. Because that's a polar molecule, it's going to have dipole-dipole forces of attraction as well as LDFs as its intermolecular forces between one molecule and another. On the other hand, PTFE, that's nonpolar because all 4 of the hydrogens have been replaced. And because it's nonpolar, it has London dispersion forces only as its intermolecular force. Okay, now on the exam, they wouldn't ask you to predict which one would have the higher melting point if you have something that's different. And here we've got dipole-dipole and LDF, and on the other hand, we have just LDF. So you have to be given one more piece of information. So let's go ahead and say that if you were given that PTFE has a larger boiling point, which it does, then which one has the stronger intermolecular force and why? So you might think that PVF, since dipole-dipole, generally speaking, are a stronger intermolecular force than London dispersion forces, you might have gone with that one. I thought that it was PVF. And if it had the higher boiling point, you would have been right. But don't argue with the data that's given to you. If you are told that PTFE has the larger boiling point, then it has to have the stronger intermolecular force. Why would that be? Similar to the answer that we just had. So the way that you would answer this question is that you would discuss the fact that PVF is polar and has dipole-dipole and LDFs. So you've identified the fact that it's polar and what kind of intermolecular forces are there. PTFE, it's nonpolar, so you've said that that one has London dispersion forces only. That's the first thing that you do. If you want to think of those as steps, identify the type of intermolecular force first, then make a comparison. As step 2, the LDFs in PTFE are stronger than the combined dipole-dipole and LDFs of PVF. We know that because we were told that the boiling point is larger for PTFE. So now come up with a reason why. PTFE has a larger electron cloud, which makes it more polarizable, just like we talked about, and therefore it has a larger, much more significant LDF than PVF does, and that explains, accounts for the boiling point. If you weren't given that information, that PTFE had the stronger boiling, or the higher boiling point rather, and you said that PVF did because it had a dipole-dipole and LDFs, then they would have had to accept that answer there. So if it's something where you're comparing something where there could be more than one answer, they'll have to give you one more piece of information. Okay, moving on to letter C, beaker diagrams. These are very popular on the AP chemistry exam. So we are given in a separate activity, a student is asked to react 100 milliliters of 0.4 molar copper 2 sulfate. And I'm going to say that that 100 milliliters, let's go ahead and put a decimal place right there so we can not worry about our significant figures being 1. There we go. So 100 milliliters of 0.4 molar copper 2 sulfate with 100 milliliters, put a decimal place there too, of 0.4 molar sodium hydroxide. 2 students each drew a particulate drawing of the overall reaction, and the drawings are shown below. So there's the beaker before mixing. And here is student A's drawing, and here's student B. So let's go ahead and look at the beakers before mixing just for a moment. We can see that there's 0.4 molar of each. So obviously the student is using each circle as representing 0.1 mole. And there is our copper sulfate, and over on this side we see that there is sodium hydroxide. So we see student A and student B's drawings, and I bet we are going to be asked which student is correct. Okay, so let's see. So there we go. That is what we're being asked. Which student's drawing correctly represents the reaction? Student A or student B? Justify your answer. Okay, so let's go back. We want to make sure that we have the right number of ions accounted for. So if I look over here and I see that the green is copper and the gold is sulfate, and I've got pink sodium and purple hydroxide. So I'm combining those 2 beakers into one. So I can see that I have 1, 2, 3, 4 of everything. So both students have still 4 of each type of ion there. So that part's correct. Now let's see. For our reaction, we're going to have to figure out what's going to be reacting with what. So we know one of the few things that you have to know in terms of solubility rules is that sodium is one of the always soluble ones. So we know that sodium is not going to be forming any kind of solid product, which neither student did that, so that's good. So if sodium is not forming a product, then we know sodium hydroxide is not going to be forming, which we knew anyways because we were given sodium hydroxide as one of the solutions. So sodium is also not going to be forming a product with the sulfate ion. So that means what we have left to react is copper with hydroxide. And that looks like what both students do. So that part's correct. But now let's pay attention to the ratios. Notice that the copper, this is a copper 2 ion, and hydroxide has a charge of -1. So we know that for every 1 copper, we should get 2 hydroxides reacting. So for every 1 copper, there should be 2 hydroxides, and there should be 1 unit of those. Let's do that again. 1 copper with 2 hydroxides, 2 units of those. So it's telling me I need 2 of my copper hydroxides, and then I still have a copper, but I have no more hydroxides to react, so I know that my hydroxide is my limiting reactant. So I'm expecting to see 2 units of my copper hydroxide, my copper 2 hydroxide in the bottom, and I should see 1 copper with 2 hydroxides. And so I can see that student 1 has made a mistake. Student 1 did 1 copper, 1 hydroxide, so they're not accounting for the charge on the copper ion. So student 1 is out already. And I can see student 2 did that correctly, that there's 1 copper with 2 hydroxides for each one of those. So I already see that it's student B. Student B is correct. Notice that student B still shows that the copper ions are in excess, and that the sodium and the sulfate ions are the spectator ions. They're remaining in the solution. I see one other thing wrong with student A, and that was if student A was trying to do a 1-to-1 ion ratio, if the student was thinking it was copper 1 with the hydroxide, the student didn't finish the reaction because they should have gone ahead and did copper to hydroxide, copper to hydroxide. So this student's got all kinds of things going on wrong. Wrong ratio, and then didn't finish the reaction. And there we go. We have student B is correct. Student A did not have the correct 1-to-2 ratio of copper 2 ions to the 2 hydroxide ions. And student A didn't finish the reaction. All right. So moving on to II, write the net ionic reaction for copper sulfate with sodium hydroxide. Okay, so I know that the sodium is a spectator, which lets me know that the sulfate is a spectator, like we just said. And so now I know that I'm reacting copper ions with hydroxide ions to make copper sulfate. And so that makes that net ionic equation pretty straightforward. On these, you do have to be very careful. You have to show the charge of the ion. Of the ion. Cu2 plus, that is copper that's dissolved in water. That is not the same thing as Cu with no charge. That's solid copper. So this is ions dissolved in water. And then we have the hydroxide ions. Notice on the AP exam, you don't have to show the states of matter. So if you didn't include the aqueous or the solid here, that would be okay. You do have to show the charges, and you do need to make sure that your reaction is balanced. So I needed to have 2 hydroxides for every 1 copper to give me copper 2 hydroxide. There we go. That was a pretty straightforward question. And now on letter III, I'm asked to calculate the final concentration of sodium. I think this should be of sodium at the end of the reaction. So we know that we started with 0.4 molar sodium hydroxide, and we had 100 milliliters of that 0.4 molar. That sodium is not going anywhere. The only thing that we're doing is adding some more, we're adding 100 milliliters of copper to sulfate, so we're adding another 100 milliliters of solution. So you could do this question 2 ways. You could realize that if you're doubling the volume, then you're halving the concentration, so you would end up with 0.2 molar, or you could go ahead and do the calculation. So you would have 100 milliliters of 0.4 molar sodium ions, which will give you there's no answer there. There's 0.4 moles of sodium. There we go. So let's go ahead and write that in. So if we have 1.1 times 0.4, that gives us 0.0, if I can get my pen to write, there we go, 0.040 moles of sodium ions. Okay, so our final concentration is going to be those 0.04 moles divided by 0.2 liters of solution, which give us 0.2 molar. So you get the same answer either way. You can do the calculation, or you can just figure through it that if you're doubling the volume, you're going to half the concentration. And that brings us to the end of your practice exam. I think you guys are going to do really well. Have a lot of fun taking a 45-minute test at home by yourself. It'll be something that you can tell your grandchildren about. So you guys were there the year that the AP exam went online. Enjoy it.